Let's look at another tool to evaluate the limits of some sequences. So this is often called the squeeze theorem, but sometimes it's also called the sandwich theorem. It's really the same thing. So I want to start by telling you a bit of intuition for this, and then we'll look at the formal statement of the theorem, and then we'll look at some examples. And so the idea is that you might have some sequence b sub n where you want to compute its limit, but the sequence ends up bouncing around a lot. Like maybe it has a minus 1 to the n in it, or maybe it has a sine or a cosine in it, or something else that's making it bounce around a lot. And so maybe you can squish b sub n between two other sequences, a sub n and c sub n, that are easier to conceptualize, and then it might help you compute the limit of b sub n. And so the idea is if we have some sequence b sub n that oscillates, we're going to find a lower bound for it and an upper bound for it, where the limit of the lower bound and the upper bound ends up being the same number L. And as soon as we can do that, as soon as we can find a lower sequence and an upper sequence that go to the same thing, then that's going to squish b sub n between the two, and that means that it must also go to the same number L. So if I draw a picture of what's going on here, then the idea is that maybe we have some sequence of numbers, b sub n, that are really bouncy overall. And so that could be really annoying if we're trying to compute the limit of this sequence b sub n. But maybe we can find really easily some other sequence, a sub n, that's much better behaved than b sub n, but it still ends up going to the same sort of point overall as the b sub n's. And then maybe we can find another sequence, c, which is bigger overall than b sub n, but it also ends up going to the same sort of trajectory in the long run. And so it might be easier to compute the limits for my sequences c sub n and a sub n. And as long as these pink and green dots end up going to the same place in the long run, then they're going to squish b sub n between them, and then we'll know that the limit of the b sub n sequence has to be the same. All right, so now let's look at a more explicit example to make sure that the picture makes sense. And so at this point, it might sound hard to figure out what the corresponding sequences a sub n and c sub n should be, but in practice, it's actually pretty easy typically. And so in this example right here, where we have the limit as n goes to infinity of sine of n over n, we already know that sine of n, because it's this trig function, it's going to be between 1 and minus 1. And so in other words, that means that sine of n over n is going to be between 1 over n and minus 1 over n for all n. And so the idea with the squeeze theorem is that we'll take the limit as n goes to infinity of minus 1 over n. That's very clearly 0. We can also take the limit as n goes to infinity of positive 1 over n. That's also 0. And then since sine of n over n is squished between these, then we can conclude that the limit must be the same. So in other words, the limit of sine of n over n as n goes to infinity is 0 as well.